Okay, so now we have covered all the major functional patterns or abstractions. The functor, the applicative functor, the monad, the monoid, and also the traversable. And now it's time to put these things to work. And in this lecture, we're going to do a little case study and look at some of the design choices that we can make when writing code and see how we can use these abstractions and at the same time also learn something new. So this lecture will culminate in what is commonly referred to as the reader monad, or sometimes the environment monad. And we're going to implement this from scratch and see how it works internally. If you want to do this in practice, you should look at the F# plus library where everything is already implemented for you. So you don't have to go through all this pain to get there. Right, so what's the problem? So a very common scenario when writing real code is the following. Suppose we have some module. I'm just going to call it stuff, in lack of a better name. And in this module, we define a type, which we're just going to call options, which is not to be confused with the option type, but this is options, and that's a record type, and it contains members like, for example, debug, which is an int, verbose, which might be a bool, maybe some min, be a float, max, float, who knows? We have this option. We have this option type where we have some parameters that can somehow control the computations done in stuff. And of course, coupled to this, we have some functions. Let's say let f. Well, I'm not gonna. Well, I'm just gonna type the signatures f, and f takes an option. An options type, it might take some data type, maybe some parameters, and it returns some capital X type, who knows what it is. I have some G function, it takes some options, it takes some, maybe it takes an X, maybe it takes some Q to return a Y, and I may have even an H, and it takes some options, and maybe it takes a Z to return another X. Who knows what these functions are? Some of them may be probably internal, so that when I call F, it's then going to call G, which might call H, and so on. But the thing that we need to look at is that all of these are dependent on having access to the options. Every single one of them. And what you end up doing is you're writing code, and maybe you have 10, 15, 20 of these functions, and you always drag this option with you everywhere you go. And it's just tedious, and you just always have this extra argument to your functions. So what can we do about it? Well, here is actually a really good and valid case for using the object-oriented properties of F#. So what we can do, of course, is say, okay, so this is one solution, of course, we just do it and just live with that. Another possibility is to say, okay, let's scrap that and then create instead a type, new type. This is now a class, type, stuff, and it's going to have a constructor, and then I'm going to have some optional arguments to it, like, for example, debug, verbose, and so on. And then, of course, I can create a default constructor for it, so that I can I don't have to even give any arguments at all. And then internally in the class, I can then say, well, let debug equals default arg and so on, and let verbose equals. And now I can implement my functions as members, not static members, but proper members with x.f, and then have it, instead of taking options, f will just take data and params return an x. And then the same for g and h and so on. Because now internally inside, once I instantiate this object, I can, like this, so I can say let o equals stuff and just use the default parameters. I can now say o dot f and give it some data and some parameters to get the result. Okay? And the important thing here is that my class is not, it doesn't keep the data, it doesn't keep anything problem specific at all, nothing whatsoever related to the actual problem. None of the parameters that I might want to change, none of the data that I want to manipulate or generate. All it has is like basically these static options that control some aspects, read-only aspects of how things are to be done. And this is important, because by doing this, I can now easily just, once I have created this object, I can just have these functions on that object. I can run list map o.f on a set of data and so on. So these are just, they work like just normal functions, with the little exception that they have access to this internal data that I have stored, global data, which I can then recreate with different types of O's with different sets of configuration parameters. So this is perfectly fine. If I had decided to say, okay, but I would also add in the constructor would keep some sort of data, then then every time I want to do something that manipulates that data, I always have to sort of use the member functions like they are like proper methods, and then I can't map easily and do all these things. So this is just a trick where I'm basically staying super functional, but I have access to some internal globals that can be configurable. So this is quite nice. This is a good approach, no question. But the question is, can we do something more functional, so that we say, okay, what if I don't want to use classes for some reason? What if I want to stay really properly functional? What can we do then? So let's have a look. So there's a trick we can play. And that trick is that we had these functions f, which I had now written with options always coming first. One reason you might want to have the options first is that you could then sort of partially apply to create an f prime where you have given the options, and f prime would only take the data and the params and the x, and then you could do the same with g and h and so on. Not really a super good solution, but could potentially be better than nothing. But there's another trick we can play, and that's actually, we're going to move the options towards the end. So we're going to create a new set here. I'm just going to reuse these guys and say that f, I'm just going to rewrite f. We would do the same for all of these, and say that f is a function. It takes some data, it takes some parameters, params, some type, and then it takes options, and then it returns some type X. And now we can look at this in a slightly different manner. I'm going to introduce a number of parentheses here and look at it like this instead. So now f is a function which takes some data and some parameters and returns a function which, when given options, can return me an x. And then this here I will actually put into a proper type. So I will just create a new type, and this one I will call reader. And it's going to be parameterized over two different types. One is I just call E, and the other one I will call A, and it will soon be clear why. And then I can say reader is, and it's a union type with one case, reader of function E to A. Right? Where this E is going to be sort of this options or this environment thing that I'm going to be able to sort of access from the environment, and the A is the result type. Okay? So now I can rewrite this F as this. Data, params, reader, options, X. Okay, so what have we done so far? Well, actually we haven't done really anything. Like this F and that F, they are isomorphic. All I've done is just hidden the fact that it's a function into this type. I've just wrapped it up into this type. But it's the same thing. So this is still, although it looks like a function which takes two parameters and returns some value, that value is actually a function value, so which takes another parameter and returns the real value, which means this is a function of three parameters returning an x, which is exactly what we had in the beginning. Nothing has changed. We have just reordered things a little bit and wrapped them up. So why have we done this? Well, a little reminder here. When we talked about functors, I mentioned that functions are functors. And just to do a little refresher, we can say map fg, where that's a function, and that's also a function. And this is the same as g composed with f. So now it turns out that functions are not just functors, there are also monads. And that's a fact that we're going to utilize. So to recap what that was about, normal function composition takes a function a to a b, and it takes a b to a c, and it takes an a and produces a c. Now, when we have a function which returns some sort of wrapped up type here, like reader or option or list or something, then we take in a normal a, but what we get back is something like a to m of b, where m is now some container function. And then we have some b to m of c. And then we give this an a, and this whole thing produces an m of c. Now, as you can see, these things don't compose, because this gives me an m of b, which I can't feed directly into to here, since this wants a B and not an M of B. And the same goes on there. So here we had this Kleisli composition, which was the monadic composition operator. And we also had, for this one, we had the shove operator, which is basically just reordering things a little bit. These two are like the pipe version, and this is the function composition versions of it. And in the background for both of these monadic things was a function called bind, which does all the heavy lifting for us. Okay, so what does this have to do with what we are doing? Well, first of all, now we have created these functions that return these readers, which are functions, which happen to be functors. And now we might want to be able to compose f and g and h and do things. So let's see what happens and see why this can be useful. So the first thing we really want to look at is create some functions to start working with these things. So the first function we want to create is something that allows us to actually run this thing. Because now if I just give f a data and a parameter, I get back this reader object. And then what? Should I pattern match on it? What should I do with it? Well, yes, exactly. So I'm going to create a function called run. Actually, we're going to remove this so we have more space. I'm going to create the function called run. Let run, and run takes a reader. This is of course pattern matching here, and I'm going to extract some f, and then I'm going to take some e, which is this environment type. So in this case, when doing this reader here for my particular case, that would be of this type options then. And what it will do is that, remember that this f here is a function from e to some a, or in our case from options to x. So this is simply applying f to e. And of course this whole thing will then return an x. So this run is a really simple function. It just strips this data type, reader data type that we created. It will just strip that so we get to the function and calls the function. That's all run does. But this is an important function because it allows us to actually get results out of the reader. So here we are doing some really pretty sort of nifty partial application in the background. So, okay, let's just bite the bullet and look at bind. So suppose we want to suppose we now want to compose these two functions, all both returning a reader of some type. So how would we do that? Well, let bind, and bind takes a function of from some a to a reader of some e and a, and it takes an x, which is a reader of e and a, so we take a reader value, we take a function to compose with the reader value, or sort of map the reader value. This could be actually return a reader of b, sorry. Right? So how would we implement this? We know that the whole thing here needs to return a reader of EB. Well, the first thing we can make sure is that we know that it needs to return a reader. So we just use this data constructor to create the reader. And then we know that the reader, the type inside the reader is a function. So I'm going to create a lambda, fun, e. And then let's see what happens. Okay. So what can we do? Well, we can say, oh, I call this x. I'm going to call this g because that makes it easier. So x equals, and then I can say run g e. Right, I can't call g directly because I need to get rid of the wrapper here so I can get to the meat of the function. So then I use the run function from up here, which just strips that. This e here, well, that's the one I have here. So I'm just going to run that. That will give me the value from this container here. So I'm actually executing the function inside there. And then, well, what then? Then I can say run again. F, which is the function I gave in here, which takes a normal value, which is the x, which I produced from there, on x, and then I give it the e again, and I wrap it up. And there we have it. There's the bind. I suggest it's sort of a little bit subtle, so sit down, pen and paper, and work it through. You will see. It works. And then we need this, finally we need this return or pure function, which is super simple. Which I'm just going to call return with a prime because otherwise F# will complain. And return, it takes some value, x, and it returns a reader, fun, e to x. So this will take any value, say 5, and create a function from some environment to 5. So it's basically a constant function. It's not doing anything. And of course, I'm not using the e, so I can do it like this. And before we look at what the whole thing, what we are building up towards, I'm going to add one more function. And that's, when we see it in action, it's almost like magic, but it's really simple. And that's a function we're going to call ask. And I'm not even going to write it as a function, I'm just saying like a value, but it's going to be a reader, which we know that is a function. And it's going to be a function from e to e. So what does this ask do? Whenever it's called, it will just return the environment. So this is the heavy lifting stuff for the reader monad. Now let's see. We need to implement a few more things, and then we can actually see how this is ultra useful and beautiful. So in order to make this sort of tractable and nice to work with, we're going to create a computation expression around it so that we can get some nice syntactic sugar and we can write clean and readable code. And we don't have to bother with the loads of lambdas everywhere. So that we do like this. Type reader builder. And then we say member x.bind, which takes some value b and a function f, and we implement that simply by using our bind fv. and then we create a member x.return, which is just our return with a prime, and then we're going to do the member x return from, which will be run. Oh, I need a value there. Return run v, I think it should be. Oh, sorry. Reader run v. So this is the one where I have the return bang in the computation expression. That's the case. Okay, so these are the three things I need to define, and then I can say let reader equals reader builder, and instantiate that builder thing to create the reader object, a reader builder object, and now we can do some cool stuff. And now this is what the moment we have been waiting for, the whole point. Because remember, what we really wanted to do was get rid of this option thing all over the place, which was just annoying. So let's look at the computation expression, how we use this thing. So now I can write like this: let x reader. So I'm just going to explicitly set the type for this x. So I'm going to say that the environment is, in my case, just going to be a string. We're just going to use a string instead of this options type. A simple environment. String, and then and some int. So this is going to produce a reader which contains some int. So I'm going to do a computation producing an integer in the environment of a string. So let's see. Then I can say reader curly brace, and now the magic happens. Remember that this x here is not really, it's a value, but it's a function value wrapped in the reader. Okay, so now I can say things like this: let bang, that invokes bind, I'm just going to say e, ask. So what happens here? Ask is this guy. What will happen here is that there will be an implicit environment when we run this thing, and ask will extract that from this in the background from this function, and we can bind it to a value. So now I have access to the environment that was given when this reader is run. So I just say ask. This looks like magic, but this is actually a function invocation, because what this let bang will do is that it will strip the reader thing over and execute this function, which will receive an environment. When this guy is run, this will receive an environment, and then it will just return that value. So this is kind of magic. And now I can just use that e. So I could say something like just a normal let n equals count, or we could just say, we know e is a string, so I can say e.length. Now I'm using normal let, not let bang, to get the length of the string which is in the environment. Then I can say something like let bang q equals reader fun e. I can print something from the environment, for example, print fun e something something, and I just say 5. So what this thing will happen here is that it will receive the environment, I can do stuff, use the environment, and in the end it will return the value 5. So Q will be set to 5. But here you just see how I can just create these readers on the fly and have the thing extract the value. So this is typically not something you would do. You would rather have functions returning reader values, and then you would extract the value that they had produced and put it here. And in the end, I can say return Q plus N. And then I can, which wraps these two integers, adds them up and wraps them in a reader. Now, okay, so now I have an X. Now I have an X, which is a reader in a string environment which contains the value 5. Well, Q plus 5, whatever, N plus 5. So how do I get stuff out of it? Well, let X prime equals run X hello. And this will give the value 10. Since this is 5 characters and I add 5 to it, so this will produce the value of 10 when I run this reader. And the whole point here is now that previously I had all these functions f, g, h, and so on, which all carried this explicit environment, this explicit options type on it. And they are now gone. And instead, wherever I need to have access to some configuration option, I can just ask. And I'll get the access to the environment. And then I can look up the stuff I need to do, and I can do my stuff and I return. So this is sort of the essence of the reader monad or the environment monad. Now, this is kind of magic, isn't it? So what's really going on here? So what's really going on here is that we have, of course, a function which takes some arguments, and it takes this environment, these options, to produce a value. And I have another function which takes some things and it takes some options to produce a value. And when I run, I take the first function when I compose these things in a chain or pipe them after each other. I take the first function, I give it the environment, and normally it would just produce a value. But now I can actually, when I'm composing it with the next function, I will pick up the environment I had, which is unchanged, and as I compose it with the next function, I feed that environment into the next one as well, and the next one, and the next one, and the next one. So there's really nothing weird going on. Like if this would say ask E and it would return E, then nobody would raise an eyebrow. But what happens here is we have just magically gotten rid of the explicit E everywhere, or this explicit options type that we had, which was just the whole point of this exercise, was to get rid of it, so we don't have to have it drag it along everywhere we go. So that was the reader monad. In the next lecture, we will start talking, I think, about continuation passing, which is again a variation on functions. And the continuation passing stuff will then lead to async and how to do asynchronous computations. And from then on, we'll just start doing really practical work, doing web servers, web client code, and so on for the rest of for the remainder of the course. So that was it. Oh yes, one more thing before we conclude. So now we talked about the reader monad, which gives us access to this read-only implicit environment via this ask function. But there's also a writer monad, which I haven't implemented. The writer is really simple. it's simply defined like type writer and of some state and some A, and it's just a tuple of an A and S. So that's just a tuple. And then, so this one is again a write-only thing. So if you implement the bind and everything for this, you can implement a function which is tell, which will write into this S. And this S, of course, needs to be a monoid so that you can append to this as you go along. So then you can read and write, and of course then you can do the thing where you combine the reader and the writer into one thing, and then you get to the state monad, which basically is, we used to have E to A, and instead we're now going to have an S to an S, AS. So there's more to explore. But once you get the hang of this, it's pretty easy to pick up this stuff. So I won't go through the examples of the writer and the state monad. They're all in F# plus, so if you want to use them, they're already there, and you can see how they have been implemented. All right, that was that.